All right, well, in this chapter, looking at why certain acids are stronger than other acids, and it will all come down to four main effects: elemental effects, hybridization effects, resonance effects, and induction effects. We'll start by looking at elemental effects. Now, when we're dealing with elemental effects, we're only looking at the element bonded to the hydrogen. That's all we're paying attention to. What element is bonded to the hydrogen? Look at HF versus HCl versus HBr versus HI. When we look at the pKa's, we see that HF, actually with a pKa of 3.2, is a weak acid. HCl, HBr, HI are all strong acids, very large negative pKa's. Note that while HCl, HBr, and HI are all classified as strong acids, HI is the strongest of these three strong acids. So HI is actually a stronger acid than HCl. Now in aqueous solution, it doesn't matter. You put any three of these in aqueous solution, they'll dissociate into H3O+, the strongest acid that can exist in water. However, since this is organic chemistry, we're not always in aqueous solution. HI is going to be a stronger acid than HBr, which is stronger than HCl. And this is mainly due to bond length. We know that as you go down the periodic table, these are all halogens getting larger as we go down. The larger the element, the longer the bond. The longer the bond, the weaker it is. So HI has a weaker bond than HBr. Therefore, HI is more likely to give up a proton. Well, what do you call something that gives up a proton? An acid. And something more likely to give up the proton is a stronger acid. And HI is more likely to give up the proton because it has a longer, weaker bond. And you see the same thing when you look at H2O versus H2S versus H2SE. The element is getting larger as we go down the periodic table, and therefore the bond is getting weaker, therefore the acid is getting stronger. With H2O having a pKa of 15.7, H2SE a pKa of 3.9. H2SE a much stronger acid than H2O. And again, it's due to bond length. Okay. Now, as we go left to right across the table, when we're dealing with these elemental effects, something slightly different happens. Because you recall that as we go from left to right across the table, we're looking at carbon-hydrogen bond length versus nitrogen-hydrogen versus oxygen-hydrogen versus fluorine-hydrogen. Recall, as you go left to right across the table, elements get smaller. Fluorine is smaller than oxygen. Oxygen is smaller than nitrogen. So based on bond length, with this carbon-hydrogen bond being the longest of these four, we'd expect this to have the lowest pKa value, to be the most acidic. But it's not. It is the least acidic. Because the truth of the matter is, when you're looking at how short nitrogen-hydrogen bond is compared to carbon-hydrogen, the nitrogen is just not that much smaller than carbon. Therefore, this bond length is really not that much shorter than the carbon-hydrogen bond length. The fluorine-hydrogen bond length really is not that much shorter than the oxygen-hydrogen because fluorine is not significantly smaller than oxygen, where it is significantly smaller than chlorine going down. So when we're going across the periodic table, since bond length doesn't change that much, its effect of the weaker bond doesn't change that much. But what does change quite a bit is polarity. Due to electronegativity difference, we know fluorine is very electronegative compared to hydrogen. Carbon and hydrogen are very similar in electronegativity. Turns out the more polar the bond is, the more partial positive charge that hydrogen has. And if it has a large partial positive charge, it doesn't take a whole lot of energy to totally break the bond to give it the full positive charge. Recall with hydrogen bonded to fluorine, due to electronegativity differences, this fluorine is hogging these two electrons. This fluorine has attracted these two electrons much closer to it, so this hydrogen is close to an H plus already. It doesn't take much energy for those electrons, which are already around fluorine for the most part, to just stay on fluorine and give up H plus. So that is why when we look at the pKa, we find this highly polar HF bond gives you a stronger acid than the CH bond, which is hardly polar at all. All right. And of course, recall the stronger the acid, the weaker its conjugate base. So the conjugate base of HF is F minus, is a fairly weak conjugate base, whereas CH3 minus, the conjugate base of CH4, since CH4 is a very, very, very weak acid, CH3 minus is a very, very, very strong base. All right. And so that's our elemental effects, and you got to get this into your head. It only comes into play when we're looking at the element directly bonded to the hydrogen that's going to be given up in the acid. We're looking at this hydrogen here bonded to this oxygen. That's elemental effects. All right. The next effect, I won't spend a whole lot of time on, hybridization effects. It tells us why alkynes, terminal alkynes, are more acidic than alkenes or alkanes. It turns out when you look at the hybridization here, recall that this carbon is sp hybridized if it's got the triple bond, which means if it's sp hybridized, it's 50% S in character, 50% P in character. Compared to sp3 hybridization, all four of these orbitals hybridized together means this is 25% S, 75% P. Well, the more S character you have, the more stable the anion is. Since this has 50% S character, the anion, when it is made, has 50% S character. Here the anion only has 25% S character. More S character, the more stable the anion is. The more stable the anion is, the more likely it is to form. So due to these hybridization effects, these terminal alkynes are quite acidic compared to the alkenes or alkanes. And it also means that while the terminal alkyne has a pKa of 25, so its conjugate base is pretty darn basic, alkanes with a pKa of 50, their conjugate base is much, much, much stronger, since their acid strength with a pKa of 50 is much, much, much weaker. All right, so that covers elemental effects and hybridization effects. We will introduce the next effect here, inductive effects, and then we're really going to start applying them with carboxylic acids, and we're not going to worry too much about the energy. When we get into chapter 6, we'll look more at these energy issues. Okay. Inductive effects. An electronegative group, such as fluorine or oxygen, are electron withdrawing. As we know, they're very electronegative. They attract electron density to themselves. They attract electrons to themselves in covalent bonds. Which means if we look at this molecule right here, if we have a fluorine attached to a CH2 attached to a CH3, we know this fluorine is pulling the electron density away from this carbon. It gives a fluorine a partial negative charge. This gives this carbon a partial positive charge. Well, this partial positively charged carbon bonded to this carbon is going to pull a little bit of electron density towards itself, giving this carbon a slight positive charge. Now, the further you go in distance from this fluorine, the less the inductive effect, which means the carbon right next to the fluorine has a definite partial positive charge. The next carbon over, a much smaller partial positive charge. If there's another carbon over, it would have an even smaller partial positive charge. Inductive effect weakens with distance. And where we really find this playing out is in the acidity of carboxylic acids. All right. So we look at CH3, C double bond O, OH. Acetic acid, pKa is 4.75. Why is it so much more acidic than an alcohol, CH3, CH2OH, which has a pKa of 16? And we could look at the energies. We're not going to worry about that. What we look at are our two explanations, resonance effects and inductive effects. And let's see, let's start with our resonance effects, and we might as well. When you take the hydrogen away, say you had this acetic acid, you take the hydrogen away from here, now you have acetate ion. And recall, when you have acetate ion, when you do the Lewis structure, it has a resonance form. And the resonance form means that this acetate ion is more stable than you think it would be. Recall from chapter 1, resonance means stability. If you have resonance forms, that means that thing is more stable than you would think. If this anion is more stable than you think it would be, that means that the reaction to make the anion is probably going to go a little bit better. This alcohol, when you take this hydrogen away, there's no resonance forms. When you take the hydrogen away from this ethanol, it becomes ethoxide. There's no resonance forms for that. Whereas acetic acid, carboxylic acids, their conjugate base is an acetate type ion. There's resonance forms. This is more stable, so the reaction is more likely to form this product than it is to form the ethoxide. Resonance means stability. Nature likes stability, so nature is more likely to form a more stable product than a less stable product, which means nature is more likely to take off this hydrogen, which means a carboxylic acid is more acidic. And there are also inductive effects. Recall, if this acetic acid has this oxygen here, oxygen's more electronegative than carbon, it's going to pull electron density from this carbon. And note, we're comparing it to ethanol right here. Both of these molecules have two carbons and an OH, two carbons and an OH. It's just this one has this carbonyl where this has a CH2. With just two hydrogens, there's no inductive effect, but this has an oxygen which will pull electron density away from this carbon, making this carbon more positive than it should be. So it's going to pull electron density away from this oxygen more than this carbon up here can pull electron density away from this oxygen. This carbon here does a poor job of pulling electron density away from this oxygen. This one does a better because it's more positively charged due to the double bonded oxygen. Which means if this oxygen had some of its electron density pulled away from it, it doesn't like that. It's going to pull some electron density away from this hydrogen, making this hydrogen have more partial positive charge than this hydrogen up here. More partial positive charge means it's more likely to become fully positive charge and break off. Okay, so how does this affect other carboxylic acids? So let's look at normal CH3C double bond OH versus ClCH2C double bond OH. That's a little messy. Let's clean it up here. So the two molecules we're looking at are normal acetic acid, CH3C double bond OH. And let's write CH2C double bond OOH here, but there's a chlorine on here. So this is a chloroacetic acid. Well, what effect is the chlorine going to have that we don't have with this acetic acid up here? Well, we know chlorine is more electronegative, so it's going to pull the electron density towards itself, making this carbon more positively charged than this carbon up here. Well, if this carbon's more positively charged, then it's going to pull electron density through the inductive effect away from this carbon. So now this carbon is even more positively charged than this carbon with normal acetic acid, which will pull electron density away from this oxygen, which will pull electron density away from this hydrogen. So while we already know that this hydrogen here has a fairly decent partial positive charge, meaning it's fairly acidic, This hydrogen down here has a larger partial positive charge. This hydrogen here is more positive than this one due to this chlorine and this chlorine's inductive effect of pulling electron density towards it. Since this hydrogen here is more positively charged than this one, it's more likely to be given up. An electronegative group down away from the carbonyl carbon of a carboxylic acid means that this is going to be more acidic than this one. Chloroacetic acid has a smaller pKa. It is more acidic than normal acetic acid. Okay. Now, the thing to remember here is this is, when we're looking at comparing these acetic acids, it's all based off of two things. One is the distance, because we know this effect gets smaller and smaller with distance. And the other thing is the electronegativity value of that element. By the way, recall that normal acetic acid has a pKa of 4.8. Chloroacetic acid has a pKa of 2.8, 2.86. So that chlorine on this carbon drops it by about 2 pKa units. So then, question, what would we have if we're going to look at the acidity of, let's use CH3, CH2, CH2, C double bond O, OH, versus, say, CH3, CH2, CHF, C double bond O, OH. Ooh, let's add another one. Versus CH3, CH2, CHBr, C double bond O, OH. Which of these is the most acidic? Well, they're all three carboxylic acids, so they have their resonance effects. They're about the same. So we need to look at the inductive effects of any electronegative elements. And we see there are no electronegative elements here, so no inductive effects. Here we have a fluorine. And we know the fluorine is going to pull the electron density towards it, which makes this carbon more positive. So it's going to pull electron density away from this carbon here. Yes, it'll pull electron density away from the carbon over here, but we don't care. We're trying to find out the acidity of the proton on this side. Well, this carbonyl carbon is more positive, pulls electron density from this oxygen, pulls electron density from this hydrogen. So now we know a fluorine, through inductive effects, makes this molecule more acidic than normal acetic acid. But what about a bromine? We know that bromine is more electronegative than carbon, so it will have inductive effects that will also make this proton more positive. But which which has the larger inductive effect, the fluorine or the bromine? The answer is the fluorine has a more inductive effect because it is more electronegative. Fluorine is a more electronegative atom, so it's going to pull electron density towards itself much more than a bromine would, which means this hydrogen is going to be much more positively charged than even this one. So this is the most acidic. This one up here with no electronegative element is the least acidic of these three, and this one's in the middle. Now, a big problem that people have is they're saying, wait a minute, what, isn't HBr a stronger acid than HF? Well, yes, HBr is a stronger acid than HF, but that's elemental effects where you are looking directly at the element that the hydrogen is bonded to. What element is this hydrogen bonded to? Here it's a bromine, here it's a fluorine. That's elemental effects. There are no elemental effects at play here because the hydrogen is bonded to an oxygen in all three of these. Elemental effects is only looking at the element that hydrogen is bonded to. Here, the most acidic hydrogen is bonded to oxygen. That's the same element, so there's no elemental effects here. With elemental effects, yes, HBr is more acidic than HF, but since there are no elemental effects here, this is just inductive effect. It is purely by electronegativity. Fluorine is more electronegative than bromine, so this fluorine would generate a stronger acid. And our last part of this chapter, what if we what about this one in here? What if we had CH3CHF, CH2C double bond OOH? How would this one compare to these guys? Well, first of all, we could say we've got the fluorine on here. We've got our inductive effect, so it's definitely more acidic than this one. This one is more acidic than this one. No fluorines, no electronegative beats on it. We've got a fluorine there. So this new guy is more electronegative than the normal carboxylic acid. We can also see that the fluorine is one carbon further away from the hydrogen. Here, this fluorine is on the carbon next to the carbonyl. Here, this fluorine is not on the carbon next to the carbonyl. It's one over. We know inductive effects get smaller the further that electronegative element is, so we know that this is less acidic than this. The fluorine on a carbon further away from the carbonyl means that the closer fluorine has more of an inductive effect, making this guy here more acidic than this guy here. This one here will have the smaller pKa. Well, what about these two? Oh, that's tough. We know that the bromine has a less inductive effect than a fluorine on the same carbon, but what about a fluorine that has less inductive effect because it's one carbon over, which means I will not ask you to compare those two. On an exam, I will not ask you which of these is more acidic because I don't expect you to know that without going much, much deeper into these effects. I'm not going to ask you something like that. But which of these is more acidic? Which of these three is more acidic? Absolutely, that question will be asked. All right, so that is it for this chapter. Next video, we'll go into chapter 4, start looking at naming compounds and looking at organic structures three-dimensionally.